Parallel computing refers to the use in combination of two or more processes, which can be threads, cores, computers, to solve a single problem. It requires to divide the workload into several processors. Uh, Parallel computing requires a parallel design of programs, which is not always trivial under the point of view of the programmer. And finally, a parallel computing in combination with distributed computing, which involves many machines, requires a more complex design because it must be parallel but also must involve efficient communication between machines and a common storage for the machines which are involved in the same program execution. Automatic conversion of serial code into its functionally equivalent parallel version remains as an open challenge for researchers. Most of the tools are either oriented to Fortran or C or C++. Some tools are oriented to conversion of serial code into parallel one, such as OpenMP or others. Others are specifically oriented to assist the creation of parallel code, such as CUDA, OpenCL, and others are oriented to distribute code created with a parallel design, such as Spark, Cham++, Boeing, etc. Literature about optimizing the execution of code along runtime, taking into account the underlying infrastructure, it means the machines, is huge. Although in general are oriented to loosely coupled application. So it means that there is a strong limitation in which what we can do with the existing tools. There are two main problems in parallel and distributed computing. The first one is the splitting. Split the original source code into a set of small pieces. And the second problem is how to distribute these small pieces of code into a set of machines in order to execute all together in parallel. So for the first program, the splitting, some tools requires the programming of the small pieces by the programmer, not automated. For the second problem, the distribution, some tools allows only client-server communication, which limits the way in your program are executed. So you need to design your program for this client-server paradigm. A very well-known example of this type of tools is Boeing, for example. So the aim of this work is to create a tool, which is name is cloudbook, that face both problems, split and distribute the code. In order and distribute the code in the set of machines in order to maximize the performance when executing, allowing the communications of all machines each other. In the previous slide, we have talked about how machines communicate each other. All machines can communicate each other, so they are not restricted to the client-server paradigm. So this is an unattended parallel compiler. And during the first stage of the tool of cloudbook, we start analyzing the source code and creating a matrix, which this matrix assists the decision to group functions in each deployable unit. So if we analyze the original source code of a program, we find different functions that invoke to the other ones. So if we fill a matrix with a number of invocations from one function to another one, we discover that there are functions that invoke each other a lot of times. So these functions should be deployed together in order to save communications. That's the first step of the cloudbook, the creation of this matrix. The codebook parallel compiler is composed of three main parts. First one, the maker, which involves the graph analyzer in charge of creating the matrix, and the splitter, which produce the different deployable units. Then we have the deployer, which assign the different deployable units to the different machine. And finally, we have the agents that are the components in charge of execute the deployable units. Cloudbook supports different language extensions, pragmas, to produce optimal code. If the programmer use these pragmas with intelligence, can increase the performance of the program. But in fact, they are not mandatory. You can create your own program, pass the program through Cloudbook, and you have a parallel distributed version of the program. So some of these pragmas are very simple to understand. For example, Cloudbook parallel is a pragma that converts a function into a parallel function. So it's this function will be deployed in all the machines, in all deployable units, and for example, with the Pragma Cloudbook Sync, you can wait to, if you invoke a lot of machines, a parallel function, you can wait to the termination of all these parallel functions. So you have some elements to produce a parallel execution, also to create global variables, also to create critical sections, and so on. So the knowledge to create these parallel programs is very reduced. You can create a program just from the beginning because you don't need a special and heavy training on Cloudbook tool. Regarding the global variables are implemented through a deployable unit which keeps a copy of the variable. So there is only one copy of the global variable. So when different machines access to this variable, creates a copy of the variable. So the global variables are, by default, are not safe because every single function when it starts its execution make a copy of a global variable that is going to be used. But during the execution, if don't refresh the global variable, it's using a old version of the global variable. So you can use global variables, but are not safe by default. Can be safe, but by default are not safe. It increases the performance. The Cloudbook global architecture is composed of three main pieces: the maker, the deployer, and the agents. The maker is in charge of produce the deployable units, and it's composed of two components: the graph analyzer in charge of the matrix and create the matrix of invocations, and the splitter that creates finally the deployable units, which will be deployed by the deployer into the agents. The way in which the deployer works is creating a file called Cloudbook. The Cloudbook file is the most important file of the architecture, and this file contains the matching between agents and deployable units. So the deployer is aware of the underlying architecture, the machines, the capacity of every machines, what quantity of memory or CPU grant to the execution of the program, and depending on this information, make an assignment or another. And this assignment is written in the Cloudbook file. Well, during the execution, we have an stats monitor which takes information about invocation between agents. And if two agents, for example, invoke each other a lot of times, it is possible to improve the matrix of the program. So the stats monitor functionality is used for increasing the performance of the program during execution. During execution, statistics are gathered, matrix are improved, and if you want, you can stop the program, make a remake of the program using this matrix, and split the program in a better way. Finally, the purpose of the distributed file system is not only for make these files accessible to the agents, it's also because the distributed file system is a way to to provide an scalability to the possibilities of the number of agents, because depending on your deployment of your architecture, if you have 10 machines, perhaps with an NFS file system is enough. But if you have thousands or millions of machines, perhaps you need another distributed file system, such as Resilio or another one. So cloudbook is agnostic respect the distributed file system you use, but needs a distributed file system. Dynamic execution takes into account two scenarios. The first one is when agents stopped or new agents are added to the infrastructure. In that case, Cloudbook assign new tasks to the new agents because the deployer has a surveillance mode. So it's taking into account that new agents are added in order to assign new tasks, new deployable units to these new agents. In the same way, when an agent stops, the deployable unit, which have this agent, relays on the rest of agents. So redeployment is performed during execution in order to continue execution, even if some agents stops. If some agents are added in real time, the execution don't stop. There are another scenario in which the performance can be improved thanks to the statistics. So during the execution, agents produce statistics that are consumed by the stats monitor. This monitor create a new matrix, improve respect the theoretical matrix created by the graph analyzer. This matrix can be used for make a remake of the program to produce new deployable units more efficient, because normally these new deployable units save communications. Because, for example, has been detected that one function invokes another one, which are located in different machines, and communication can be reduced if both functions are joined in the same deployable unit. So that's what the maker do when we use the new matrix produced by the stats monitor, and the performance can be increased a lot. I'm talking about 10 times faster, for example. It's normal when this feature is used. Regarding the results, communications among agents have a price in terms of performance, because the communications involve timings and this reduce the speed of the program. But if the tasks are involve more work than communications, more CPU than communications, definitely the benefit is very high, even linear. It's approximately linear. In the bottom, we have the graphic of the end body, the classical program end body, and the different number of bodies are represented in the horizontal axis. And Cloudbook save a lot of time, more or less with 4 machines, is the speed it 4 times faster when the number of bodies are enough. On the right side, we have a table with another application in intrusion detection system application, which analyze files in order to prepare information for a learning algorithm. And in this table also we have a approximately linear improvement of speed. For recursive problems, stack size takes benefit from the number of machines. The recursive problems are not speed up, but the stack size is increased linearly. If you have 4 machines, you have 4 times bigger the stack size. So you can go deeply in the recursion. The conclusions. Cloudbook makes parallelization, but also is aware of the number of machines and characteristics of every machine involved in the execution. So we solve both problems, the production of deployable units, the splitting of the code, and also we produce a code that takes into account the different capacities of the different machines involved in the execution. Additionally, the learning process is very fast because you don't need a lot of knowledge to use cloudbook. The creation of parallel programs is quite easy, and the limits of the efficiency of these parallel programs depend on the communications of the of internally communication of the machines, the agents involved in the execution. So the main advantage is of the provision of automatic splitting, the generic, not simply bounded to master-slave based programs, because allows communication each other, not only master-slave communications. It's valid for distributed and parallel environments, and, and it's able to dynamic redeploy the software when one machine stops or new machines are added to the cycle of machines in execution. And finally, no less important, low required level of knowledge. So all these main advantages makes cloudbook a very good option, not only as a tool, but as an idea to to produce parallel and distribute code for any language. In this case, is created for Python, but could be created for any other language. That's all. Thank you very much.